and was a postdoctoral scholar at Stanford subsequent to that. So without further ado, Vivek, please go ahead.
So I can't share still for some reason.
Yeah. Are you
Yeah,
able to unshare Pedro?
I tried. It says that I haven't. Okay, sorry. Yeah, there you go.
All right. Please go ahead, Vivek.
Can you see this?
Yeah.
Okay, cool. Awesome. Thanks for the introduction. I'm very excited to follow Pedro because, in some sense, he made a lot of points I wanted to make, which, and I'm going to present a slightly different perspective of essentially some of the points that came up in the discussion after his talk. So this is joint work with my collaborators and students listed below. And the starting point of this work is really this question. Neural networks seem to be so good. They seem to be winning awards, running the 1 mile marathon, 1 minute marathon and all that. So um, what are they really doing? I mean, just because, and at a more abstract level, if I give you a machine that makes successful predictions, does this mean that this machine understands and the system that it's working with? And I'm going to argue not necessarily. And let me give you an illustration from this event, this eclipse that took place in ancient Greece in 585 BC. It's just one of these run-of-the-mill solar eclipses. But the reason this was an interesting phenomenon is this guy, Thales of Miletus, he successfully predicted the eclipse before it happened. There's evidence that shows that he didn't know how to do it by himself. He learned it from Babylonian astronomers and so on. But that's not the point. So what we have here is Thales having predicted an eclipse. Can we say that they knew how eclipses worked just because they were able to make a prediction? And the answer, it's pretty conclusive that no. The first understanding of how eclipses work, the cosmological arrangements, came about a century after the existence of Thales. So using modern terminology, what Thales and others did is essentially they data mined observations of cycles in eclipses and said, oh, if there is a lunar eclipse today, every 19 years from now, about 19-ish years from now, there will be a lunar eclipse in the same place. If there's a solar eclipse, it's the same cycle, but there's some uncertainty because the solar eclipse is not seen everywhere in the world. But they had no clue about the Earth and the Moon and the Sun being organized in certain ways, which we know now. I'm going to argue that neural networks are doing something like that. They're finding patterns in data. That leads to frighteningly accurate predictions if you look at only benchmarks. But just because a system makes an accurate prediction does not imply that it actually understands anything about what's going on. And this is kind of related to Pedro's point at the end of this talk. In fact, what I think neural networks end up doing is they latch on to spurious patterns. Not necessarily always, but they can latch on to spurious patterns in the data. And this is really a recipe for failure. Let me give you a couple of examples of these kinds of failures. So here's an image, and there's a task called visual question answering. You're given an image and you're asked to answer a question about this image. So this is a cluttered desk. And let's say if you give the question, where is the penguin? This system says with like 65% probability that there's a penguin on this desk and it's on the table. And if you're still looking for the penguin, let me help you out. There is a penguin on the table. And this seems amazing. I mean, most people don't spot the penguin, and this seems really cool. But if you literally take the same system and ask for the same image, you can ask, is there a penguin on the image? In the image, and the system says no, with 100% confidence. So we have this weirdly sort of a quantum penguin here that both exists and does not exist. And of course, only one of these answers can be correct. Unfortunately, today's state of the art is innocent of any kind of theory of the world. Let me give you another example. This is a task that I like to work with called natural language inference, and I'll be using this task as a running example through the talk. You're given two sentences, a premise and a hypothesis. The premise here is before it moved to Chicago, the aerospace manufacturer Boeing was the largest company in Seattle. And the hypothesis is given the premise, can we say that Boeing is a Chicago-based aerospace manufacturer? And you can have either the premise entails the hypothesis or the premise contradicts the hypothesis, or they are unrelated. so which is called neutral. So if you give this pair of sentences to one of the state-of-the-art systems today, it says that it's quite likely that the premise entails the hypothesis, which seems pretty cool. I mean, this may not seem like a very complicated sentence, but it involves a few jumps that you have to do to get to the answer. Again, seems pretty impressive. But it's super easy to make these systems fail. So let's take these three sentences, P, H, and Z. P says John is on a train to Berlin, and H says John is traveling to Berlin. So clearly, P entails H. Most people would agree that if John's on a train to Berlin, he's traveling to Berlin. Then you can ask, what about H and Z? H contradicts Z. If he's traveling to Berlin right now, he can't be having lunch in Berlin at the same time. So H contradicts Z, and the system would predict that also. Now you can ask, what about the relationship between P and Z? And imagine that there's a system that says there's no relationship between P and Z. Clearly, there's a problem. A system cannot simultaneously hold these three beliefs. If P entails H and H contradicts Z, then P should contradict Z. This is an invariant that we can write down in logic without actually knowing which sentence we are talking about, which three sentences we are talking about. And yet, a reportedly state-of-the-art natural language inference system that gets 90+% accuracy or something on the benchmark violates this invariant on like more than half of a large collection of triples. So it's clear that these systems are essentially just pattern matching without understanding what's going on. So the question in the context of this example is, can today's neural networks use theory of this kind in the form of invariants in order to guide their how they fit the data? So the starting point of this work that my students and I have been doing for a few years now is really, when we build neural networks for all sorts of tasks, are we really modeling problems, or are we modeling just the benchmark test sets? And the challenge is we need modeling strategies that somehow rely on a theory, or at least, or maybe even better, maybe expose a theory. Because otherwise, I think we're just guessing equations in high dimensions without understanding anything about what they're doing. So the contrast here is, are we behaving like Thales, who guessed equations in the eclipse space, or are we trying to get work with the philosophy of the underlying phenomenon and work with that? So I would like to argue that instead of the problem, the reason we are stuck in this equation guessing game is because we seem to be forcing ourselves to only learn from labeled examples, and we should be learning from knowledge instead. What do I mean by that? I claim knowledge is data. I mean, I don't think anyone would disagree with that. More importantly, today's machine learning is heavily based on this idea of having to annotate examples and building models on top of labeled examples. But good data sets are expensive to make. They take expertise, they take time. It's not easy. Sometimes it might be easier to write rules about what we expect a model to do. And this could express invariance about the problem, or it could express inference rules about various parts of various components of the system. These could be stated as universally quantified statements, like if two sentences don't have any words that match each other, imagine that match is a predicate, then the two sentences cannot entail or contradict each other. And I would like to train models that satisfy this rule as much as possible. And how do you do that? So where can knowledge be involved? You can think of injecting knowledge into a machine learning system in multiple places. You can think of it as influencing model design. Knowledge can change how we train the model by changing the kind of objective that we're optimizing, or they can rules can enforce congruency in predictions. The last part is really structured learning and prediction. Pedro spoke about that, and it can be difficult to you might have to deal with computational expense, inference issues and such things. Another line of my work involves structured output and structured output prediction, and I I spend my other life doing that, but this talk is all about the first two things. How do we change the model, a neural network model design with logic, or how do we change the way in which models are trained with logic? In order to kind of unify these two worlds, we have on one hand neural network land, on the other hand we have logic land, and I would like to merge them. Let's look at what each of them give us. Neural networks are essentially differentiable compute. There are fantastic libraries, massive industrial backing, and essentially it's super easy to use. High school students start using PyTorch before they know anything about machine learning, and that's the world we live in. On the other hand, neural networks are really hard to supervise, except we are labeled examples, and there is some magic that happens inside them through all these dozens of layers of anonymous units that are in them. First order logic is expressive. You can state rules easily, and it's a natural way in which domain experts can work with a problem. Unfortunately, logic is not differentiable, and as a result, the whole infrastructure that exists for neural networks doesn't really work well with logic. What we want is, of course, both of these things. So I'm going to talk about a direction that my students and I have been playing with, which seems very promising. And there are some caveats that maybe I'm going to hide, and maybe some of you will notice. There are three challenges when we want to unify logic with neural networks. Neural networks, as I said, are full of anonymous units of compute. What we need are somehow to, to start the process, we need to connect the predicates in the rules that we are writing with neural networks. The second thing is we need to make logic differentiable, because we have essentially given ourselves a design constraint that we are going to work with this differentiable compute. The third one is how do we use such differentiable logic? So let's go through these one at a time. So I claim that all neural networks expose some interfaces in the form of nodes that have some external meaning. I'm going to use natural language inference as an example to illustrate this. So imagine you have this black box. This is black box that takes two sentences. John is on a train to Berlin, and John is traveling to Berlin. And it does something, and it makes a prediction that the premise entails the hypothesis. Well, even though the entire internals of this network might be opaque, we do have three things that are accessible to us: the inputs and the outputs. In this case, there are three because there are two inputs. So we can think of any neural network as expressing a predicate over the inputs. So in this case, you have a predicate entail, which has two arguments, premise and hypothesis. We can also think of any deterministic properties of the inputs as predicates that we have access to. So these form the interfaces that we have. Sometimes we can open up the black box. Some internal nodes in a network have some meaning by design. So I could have a node here, for example, that's an attention node that says that that you can think of it as what's the probability that the word traveling is aligned with the word train. I can think of that particular node as a soft probability for this predicate, or a soft version of this predicate, align, train, and travel. So we get these, not every node in the neural network might have a name of this kind, but some nodes in the networks might have names that we can work with. This is an important component that we'll need. I'm calling them named neurons. These are nodes inside a computation graph that have some external meaning. Named neurons give us the vocabulary for writing down rules. So you could have a neuron, a neuron is just a fancy name here for some function that gives you a probability for an alignment between these two phrases. And I can treat it as if I'm working with this predicate called align. So I'll use lowercase for neurons and uppercase for predicates. So that's the first challenge. How do we bridge predicates in the rules that we have with neural networks? Well, we restrict ourselves to writing rules about named neurons. The second question is, how do we make logic differentiable? There are many approaches for this. And the idea that we've been playing with involves triangular norms. They provide systematic relaxations of logic, and some of them are even continuous, and some of them are sub-differentiable, and so we can work with them. So if you have these four the standard Boolean operators, their inputs and outputs live in the set 0, 1, and I can relax them to using different named relaxations or even otherwise. And each operator becomes a function that we can now plug in to a neural network. And what it gives us is functions that are essentially in the range 0 to 1. One cool thing is the Lukasiewicz relaxation is essentially built out of rectified linear units. So any self-respecting neural network library today has this stuff built in. So we can just use this out of the box. Just as an example of how these relaxed operators work, we can look at the conjunction. If you think of the conjunction as a function that maps 0, 1 to the 4 the standard definition of the conjunction, we can essentially connect the space between this thing in any sort of a monotonic way, and each of those gives you a relaxation, and each of those is a different relaxation. All these relaxations agree with the definition of the conjunction at the 4 boundary points, and internally they are just a surface. There's a question of which of these is the best to use, and we found that it turns out, for reasons that I'm not entirely happy about, the product seems to be the best relaxation, but we can keep that discussion offline. Anyway, so the short version of this thing is, if you want to use relaxed logic, using a T-norm relaxation seems to be promising. So next question is, how do you use these relaxations? What can logic do for neural networks? Essentially, one way or another, either through what I'm talking about or through standard structured models, knowledge introduces inductive bias, and that's important. In the specific context that I'm talking about, we can introduce inductive bias by essentially modifying the network architecture to be more amenable to satisfying the constraints we have, or by essentially imposing a preference during the optimization process that we have, so that models that violate constraints are penalized. So I'm going to give cartoon examples of each of these things. So let's see how we can change the network architecture. So imagine that we have a neural network with 2 layers, and actually many layers. I'm just showing 2 of them. There's a layer of the A's and the layer of the B's. And there are many layers in between them. In particular, I'm going to focus on this node here, B1. B1 depends on some inputs X that are not shown here. In addition to this network, let's say we also have this rule that says A1 and A2 implies B1. So that involves these 3 nodes here. So these are the these are the predicates that we have, and this A1, the lowercase, these are the named neurons. Well, I can convert the left-hand side into a soft function using Lukasiewicz logic, and I'm going to call that D. It's a function that if D takes a higher value, that means the left-hand side is more likely to be true. I can replace B here with a constrained node, essentially adding a short circuit from the A's to the B's through this distance. I'm calling these D's distances. And introduce one extra input to that particular node here. If you want to kind of go over this in a little bit more detail, imagine that the row on the slide is a positive number. If D is high and rho is high, then if A1 and A2 are true, then this B1, the expression inside this thing becomes large, and as a result, B1 becomes closer to 1. B1 becomes larger. If A1 and A2 are false, then, well, the A1 and A2 have nothing to say about B, and the value of B depends on whatever was coming from the W and X. So we are going to replace such node, the original node B, with an augmented node B prime, and we'll do this systematically. This is just a cartoon example. You can imagine that we can essentially perform this operation. It's a compile time operation. We can do this before any training happens. Give me a neural network, give me some rules, and I'll marry them together to give you a neural network, an augmented network that you can use. There are there is this additional term rho here, which we think of as a hyperparameter. You can think of it as deciding how strongly is the constraint enforced. If rho is infinity, then B1 prime is going to essentially ignore what X says. It's not going to look at that. If rho is 0, it's going to ignore the constraint. Okay, so that's one version of things. We can change the network architecture using by changing using the rules. The other way of thinking about it is we can keep the network that we have. Sometimes we have neural networks where we don't really know what's happening inside them. We don't really get to control them. Instead, we can regularize learning, and let's see how that works. To see that, we need to kind of think about labeled examples and knowledge in a uniform way. All labeled data and constraints together can be written as rules of this kind. L implies R. For example, I can write rules like if given 3 sentences, if the sentence P entails the sentence H, and if the sentence H entails the sentence Z, then P should entail Z. This is a universally quantified rule. It's of the form L implies R. If I have a labeled example, let's say I have a pair P and H that's labeled with something, let's say entail, I can write this as true entails implies P comma H. So it's of this form L implies R. So all my data and all my knowledge can be written as this one thing. So anything that we build on top can assume that we have rules of this kind. Importantly, knowledge that we have doesn't really depend on labeled examples. We can just use unlabeled data and work with these rules. Now, you remember that these rules are written in terms of these predicates that we have some probabilities for from the neural network. The goal of learning is to find a model that makes all these rules true. That's what we want, because we want the knowledge to be the constraints to be satisfied and all the labeled examples to be to get the model to assign a label that the data says. So we want all the rules of this form to be true. We can't do that because that's a discrete search problem. Instead, we want to find models that maximize a t-norm relaxation. At this point, you can use whatever t-norm you want. You can use any neural network you want. You can use any library and any optimizer. A cool observation that we found is if you use the product relaxation and just have labeled examples, what we end up getting using this formalism is the popular cross entropy loss, which is a different way, at least the third or the fourth different perspective on cross entropy that I've seen, which is neat. All right. In the interest of time, I'm not going to show you a whole bunch of results, and I'm just going to give you a flavor. So do these rules help neural networks? Just one example, given the running example that we've had, imagine that we want to penalize a model that makes these kinds of these 3 beliefs, that holds these 3 beliefs simultaneously. I can write transitivity constraints of this kind. For example, if P entails H and H entails Z, P should entail Z. I can also have another constraint that says if a sentence contradicts another, if P contradicts H, then H should contradict P. And this should be true for all P and H. We can literally just compile these rules into regularizers and feed it into an optimizer and give it to these state-of-the-art models based on BERT or pick your favorite. And we found that I'm not going to go over the details. I'm just showing a plot that measures how badly do these models fail. Blue is the original model that was not aware of these rules, and red is the constrained model. And the horizontal axis here is adding more data. First thing is, just adding more data does not mean that the model gets better, which is in some sense anathema to how some people approach this. Just throw more data, models get better, and it turns out models get better only from a certain perspective. Through adding more data does not necessarily mean we get better models. If you want better models that are more in some sense logically meaningful, or they agree with any invariants that you specify, you need to actually ask the models to do that. And that's the second point. These kinds of logic-based regularizers seem to help with consistency without, interestingly, adding any computational overhead, because we can just piggyback of all the improvements that have happened in industrial strength neural network libraries. A more broad summary of some experiments that we've been playing with. We've had successful experiments across multiple different tasks for both ways of introducing knowledge across natural language inference, reading comprehension, some work involving digit recognition and such things, information extraction. The general flavor is when we have less data, adding knowledge gives you better statistical models. And using these kinds of approaches, we can inject invariances into learned systems, which surprisingly don't seem to be learned even when we give a lot of data. So let me start wrapping up. I started the talk by asking, does successful prediction imply understanding? And I don't think it does. And Thales provides a nice counterexample. And if we don't think of the underlying problem and just treat it as a pure end-to-end black box learning, we can have systems that can be pretty lousy in annoying ways. What we need are systematic approaches that integrate symbolic knowledge with neural networks, because knowledge gives you inductive bias, and inductive bias is necessary when you don't have a lot of data. For the last few years, my students and I have been playing with this idea of using relaxed logic, and it seems to be a really promising idea. Thanks. I'll be happy to take questions.
Thank you, Vivek, for a wonderful talk. Let me clap for everybody. Beautiful. Questions, please. Anybody? Okay, so let me ask you a few questions. So you talked about this relaxed logic. There were three forms, I think: product, Godelian, and Lukashevich logic. And so you mentioned that using product was better than the other two, or in some of your experiments?
Yeah, so this was interesting. Interestingly, this thought came into this question that I think, if I remember right, it was following a conversation with Pedro at some Neurex or something, where we were wondering, like, what do these relaxations actually mean? And I started playing with, okay, let's not worry about what they mean. Given that there are so many relaxations, is there one that's better than the other? So it turns out that none of them are actually sound, because they essentially give up on certain axioms of logic. But in practice, the product relaxation seemed to be the best, just in experiments, because it offered better gradients. So it was more of a pragmatic reason why the product relaxation was better. There was another sort of a less empirical reason why the product was better, but according to that, essentially by asking which relaxation preserves the consistently assigns high values to all tautologies, and of course all of them fail, but some fail worse than others, and product and Lukashevich were better than anything else. But it's really a practical point. In practice, product works better simply because the gradients are not zero in a large part of the space. Lukashevich has this constant here, and that essentially gives you zero gradients, and that leads to learning not really working.
Okay, and I had one more question. So you mentioned that you can do this surgery to the neural network before training and add this logical nodes, if you will, right?
Mm-hmm.
That augment the, this picture. This is, I wonder how you do that though. Like, how do you exactly go about modifying the computational graph? Is there an automated compilation that you can do from rules to modifying the network? Or
so the version that we did for this, so that's a good question. The version that we did for the paper that we wrote on this, the automated compiler, was a grad student. Um, I'm still hoping that I can convince someone to uh, make this an automated process, because it is really just mechanical. Right now, I'm using this really cool tool called Graph Student.
Any additional questions? If not, thank you again, Vivek, for a great talk. Thank you.
Thanks.
Mark, would you like to go ahead and share your screen? So while Mark does that,
Sure.
let me introduce Mark. So he's a